Welcome, everyone. Pleased to have you here with us today for episode 94 of This is CDR. This is CDR is an online event series presented by OpenAir to explore the range of CDR solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals. OpenAir seeks to advance at every level of government here in the US, as well as in national and subnational jurisdictions globally. My name is Toby Bryce, based in Brooklyn, New York, and I work on policy and market development with OpenAir. If you haven't done so already, please introduce yourself in the chat. Tell us where you're zooming in from, if you'd like what your affiliation is in the CDR sector, and make sure you direct that message to host and panelists, sorry, to everyone, not just host and panelists, so that everyone sees the message. Quick background on OpenAir, if you're not familiar with us, we're an all-volunteer network dedicated to the responsible advancement of CDR. We are a global community. We work on shared open source missions around the world in areas of policy, innovation, communications, and activist market development. My colleague Megha Ragavan is running the chat, and she'll put some links in there to give some background on our group. There is a join link where you can fill out a form and get involved with what we're doing. Here's a sort of a graphical slide representing the range of missions that we have ongoing. I'd say there are a few dozen active missions. We also, again, we're an open source platform. So if there's something you're interested in, you can kind of get involved and build a team and start something yourself. So it's really intended to create again, a platform so that we can work together to advance CDR in a range of different project types. As always, one quick mission update. Our Massachusetts state level CDR procurement bill, the CDRLA, S2096, sponsored by the amazing Senate Majority Leader Cindy Cream in Massachusetts, has advanced out of committee. It's doing really well. There's some really great prospects for it this year. If you happen to be in the state of Massachusetts, we could really use your help in terms of contacting your local representatives and asking them to support the policy. So please reach out to us, send me a message, or you can message us here on the Zoom. And we would love to get some help with this bill because it does have a chance of passing this year. As always, we are going to define our terms. This is a definition of CDR from a great resource called the CDR Primer. It is also essentially the same definition that the IPCC uses, so we think it's a good one to work with. CDR is purposeful human activity to remove CO2 from the atmosphere and durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. Really important whenever we talk about CDR to shout from the rooftops repeatedly over and over, loud and clear, that CDR is in no way, shape, or form any sort of substitute for rapid reduction of global greenhouse gas emissions. We need to decarbonize the global economy, reduce emissions as quickly and as completely as possible, full stop. CDR is in no way a substitute for that. It is in no way an excuse not to do that. That emissions reduction is 90+% of our climate work. If we don't do it, CDR will have no meaning because the climate will be in a grave state. That said, there is clear scientific consensus that CDR is also needed alongside emissions reductions, and it's going to be needed at massive scale by mid-century, billions of tons per year. We don't know exactly how many billions, but billions of tons a year, which is a massive quantity. We're currently at tens of kiloton scale, depending on how we're going to count the CDR that's happening. And we need to start working on CDR now in parallel to this priority of reducing emissions so that we are at the scale necessary by mid-century to neutralize the greenhouse gas emissions that we can't eliminate in a climate relevant timeframe, so we can reach net zero in a climate relevant timeframe. And then in the second half of the century, there are trillions of tons of anthropogenic CO2 in the atmosphere that we're going to need to start removing those legacy emissions so we can restore our climate to a safer and healthier state. So that's why we need to do CDR. We need to start working on it now. It's not an excuse not to reduce emissions, but we need to be working on it in parallel. And that's why we're here. That's the whole context for this show. And I'm going to hand it over to my colleague, Megha Ragavan, who's going to talk a little bit about the run of show and then introduce today's presenters. Megha, hey.
Hi, I'm Megha, carbon OpenAir member based in London, and I work on carbon removal policy and market development as well. So just before we begin, we're going to start with a short presentation that will be followed by questions and then we'll do moderated audience Q&A. So please type the questions you have into the Q&A box. It's separate from the chat box, so please find the correct one to help us manage that better. We are recording the event, so we'll also send the video link out to all of you who registered, and we'll be posting it to OpenAir's website and YouTube channel. All right, this week we're very pleased to welcome Dan Maxbauer and Sean McCauley from Alkali Earth to present and discuss the company's novel process which delivers high-quality, permanent, and verifiable CDR through optimized application of alkaline industrial minerals in gravel roads. Dan is Alkali Earth's co-founder and science lead. He's an assistant professor of geology at Carleton College, and he has expertise in mineral weathering and carbon cycling, along with past experience consulting on carbon removal methodologies and project review with Verra, Frontier Climate, and XPRIZE. Sean is Alkali Earth's co-founder and business lead. He is a Carleton College geology alumnus, PhD geochemist, from Cal Berkeley, and has spent a long career working in consulting and private equity with large corporations such as McKinsey, TPG Capital, Target, and Charles Schwab. So when you guys are ready, feel free to come on.
All right. Thank you. Let me get my slides up here. Thank you. Yeah, thanks for the opportunity to be here. We're big fans of the show and have followed it for a long time. And it's exciting to be here to be able to tell you a little bit about the work we've been doing at Alkali Earth. And as you said, I guess I should say I'm Dan. Sean will be talking a little bit after me. And at Alkali Earth, we're trying to deliver permanent verifiable CDR through carbon mineralization in gravel roads. And to start, I wanted to just give kind of a high-level overview of what we do. We work closely with a supply partner who handles raw slag piles on site at steel mills. We can mix and blend those different types of slags together to create an aggregate product that we can crush and grind down to particular grain sizes, transport it to a job site. It gets spread and surfaced into a gravel road, or often sort of industrial parking lots. So the image on the right of a finished surface is more like an industrial parking lot, is a typical type of job that we can deploy. And once that surface is in place, passive mineralization and weathering reactions start to remove carbon from the atmosphere and store it durably within the aggregate layer as new carbonate minerals. And our work sort of begins with monitoring the carbon removal over time. I thought it was important to say a little bit about steel slag and what it is and why we think it's an ideal material to utilize for carbon removal. Steel slag is a mineral byproduct from the steel industry. So when you produce steel, no matter how you make steel, you're generating slag, which is effectively a lot of the light elements that don't get incorporated into the steel that's being produced. So you can picture a big molten pot. You have a lot of things that you're adding when you make steel, and the lighter elements sort of rise up to the top of the molten pot, and that's where the slag forms. There's different types of slags. I'll say a little bit about that in a minute, but all of them tend to be rich in calcium and magnesium, silica, and to some degree iron as well. And the key features in terms of carbon removal is that steel slag has a really high capacity to remove carbon. So when you look at the potential for how much could 1 ton of steel slag remove, it can be quite high. That's dictated by the calcium and the magnesium concentration or content of the material. And it's similar in many ways to sort of olivine or other ultramafic rocks that are rich in olivine with high amounts of calcium and magnesium. But what we really like about steel slag is that the reactivity is typically much faster than most natural rocks and minerals. So these materials react very rapidly because they're formed of many sort of metastable, poorly crystalline minerals. Because when you have your molten slag and it gets dumped out, the cooling rates are exceptionally high, and it makes it difficult for really crystalline minerals to form. And so there's lots of amorphous material. There's other silicate minerals, but there's also a pool of minerals called hydroxide minerals that react very rapidly. So we've come to really like working with steel slag and think it's a great product. And hopefully sort of we'll show you some examples of how we've been able to study it as we go along here. I wanted to give a quick overview as well of weathering and mineralization and sort of differentiate the two processes. Having watched a number of these presentations, I know that this audience might be pretty familiar with these concepts, but thought it was worth going over that sort of the minerals that are in steel slag, calcium and magnesium bearing hydroxide, silicate, and amorphous phases, all can react with and remove CO2. And the first set of reactions that's occurring in our roads is something I think of as weathering reactions, where you have a crystalline mineral, in this instance, a calcium silicate, that reacts with CO2 and water, and it's releasing a cation, and it's generating new bicarbonates, sort of a dissolved form of inorganic carbon. And so in this reaction, CO2 is removed through conversion into a dissolved inorganic carbon phase of bicarbonate. Applications of enhanced rock weathering, for instance, in agriculture, are trying to enhance reactions like this and to generate the release of new calcium and magnesium base cations and generate new bicarbonate. In our process, we also follow that up with carbonation reactions. So these are new carbonate minerals that are forming, and so the CO2 conversion is from gas phase or dissolved phase into a new carbonate mineral. And the reaction shown here can either use the byproducts of weathering, calcium and bicarbonate, to form a new carbonate mineral, or that reaction can happen directly with hydroxide minerals, in this case, calcium hydroxide reacting with CO2 to form a new carbonate mineral. Carbonate minerals ultimately are sort of representing the end state for carbon removal using these mechanisms, both in our sort of this process and in the natural geologic carbon cycle. What we think is really important is that they're also sort of easier to measure when you have a solid phase mineral accumulating within an aggregate layer. You can return and make measurements of that accumulation over time, which we've come to favor in this type of application. To give you a sense for how reactive the materials are, we like to show this graph. This is an example of a closed chamber monitoring the CO2 concentration from ambient levels of about 500 parts per million indoors, reacting with our aggregates. So we put some of our aggregate into a closed chamber, allowed it to sort of scrub the CO2 in the headspace. This is just dry aggregate going in, scrubbing CO2 in the headspace down to about 80 parts per million. And so it's really is reactivity you can sort of monitor in real time, and it's allowed us to do experiments where we can work on optimizing and trying to increase the carbonation rates of these materials. Okay, so to go over our process just a little bit in more detail, to sort of connect the dots on a few things, we're working with different types of slags that come out of the steel industry. For now, we're working with EAF slag, which is electric arc furnace slag, and LMF slag, which is ladle metallurgy furnace slag. You can think of EAF as sort of similar to sort of a vesicular basalt. It looks kind of like a volcanic rock. And LMF is really high in calcium and magnesium, and a very reactive product. And so we take these two different materials and we can blend them together in different combinations and at different grain sizes, and we can deploy them as an aggregate for building road surfaces or parking lots. And once we have these materials on the ground, they have exposure to CO2. And it's worth pointing out it's exposure to atmospheric CO2 that can diffuse into the road, but it's also exposure to CO2 that's fluxing up from the soils and being released from the surface of the soil into the aggregate layer. This depends on the job site, but it's another source of CO2 that we were able to remove in our projects. And once the CO2 and rainwater start to interact with the minerals, there's weathering reactions that are leaching calcium and magnesium from silicate phases. There's reaction with calcium and magnesium hydroxides. And because our aggregate layers are a high pH product, they're facilitating the formation of new carbonate minerals. For a lot of that alkalinity that's generated leads to new carbonate minerals forming. And the formation of those new carbonate minerals helps to sort of cement the surface together, so it creates a more cohesive gravel. And that makes the road surface pretty durable. So a lot of gravel roads, it depends on climate and product, but a lot of gravel roads have to be regraded annually or even more frequently than that. And these surfaces often tend to go ungraded for 5 to 10 years because of the durability that you get when you cement the surface with new carbonate minerals. In terms of our process, so we're not going to go through like an LCA or a TEA analysis today, but our process boundary is set with what I kind of just went through. So from the point we start handling slags on site with our supply partner at steel mills, to the point at which we have a deployed aggregate layer accumulating solid carbonate minerals in the on site. That's our process. The notable thing that we're not including is the slow loss of mobile cations and alkalinity that's leaching below the aggregate layer. It almost certainly would be additional carbon removal that these materials are generating through weathering reactions. But because of simplicity with measuring the solid phase, we're focusing on that for now. And Sean will say a little bit more about a research site that we have planned for this coming spring and summer, and monitoring leachate and understanding that part of the system better is sort of a goal of ours over the next year. Okay. So why gravel roads? There's really two main reasons, one of which I've already hinted at, and that's the ability for us to directly measure the carbon removal for our MRV approach. We felt really strongly as we sort of waded through ideas on what to do for carbon removal that this application offered a viable pathway where we could be measuring all of the removals that we're sort of certifying and verifying. And so we felt good about that, the ability to go out and collect sample of the carbon that's accumulated within the roadbed. There's also existing markets. So aggregate markets are really large, and steel slag competes with natural stone and natural rock in these markets. And so we didn't invent the use of steel slag in road aggregates, but we felt like the market has everything we need to sort of scale projects, and it's sort of primed for optimization. So using these materials in a smarter way is something we're really working on over the next year or two in our company. And Sean will say a little bit more about that as well. But one example that this picture sort of highlights is this is a road surface towards the top, and you're looking at sort of the side of the road. It's hard to see the angle. But these large clasts down here at the bottom are large clasts of EAF slag that are left sort of as the size of a softball or larger. And those are being used as road base. So one of the uses for the materials is as road base. We're trying to understand and learn more ways how we can divert and show sort of incentive to divert materials from that use case into a higher carbonating use case as one way we can sort of optimize the use of these materials. Okay, other ways we're thinking about optimization. We've been doing experiments indoors using sort of closed chamber with CO2 sensors to monitor removal rates. And we've been able to monitor removal over time. So this graph shows net CO2 removed in aggregate across almost 5 months now. And we've been manipulating experimental conditions to try to agitate and activate reaction in these aggregate materials in conditions that are sort of mimicking roads. So thinking of variables we might be able to tweak and control in the field as a way to sort of push and optimize the carbonation rate. And you can see our sort of more control versions are lagging almost 2 times behind the more agitated versions. And these rates, 4.5%, is starting to approach, and just in 5 months, starting to approach rates that would be meaningful if we can get to in the field. And certainly this looks like it's continuing to go up. And so we're excited about the opportunity to try to optimize these rates and increase them for our future projects. Because there's existing markets, we've also been able to get out and get into the field to sample places where slag aggregates have been used for roads and parking lots. And importantly, most of these deployments are non-uniform, so they have variable layer thicknesses, differences in compaction, differences in the aggregate blend that was used. And across different markets in the US, there's also variation in climate. So we have the opportunity to we don't have to necessarily wait to understand how these materials behave with different deployment characteristics. We can go out and we can measure it. And so we've done one large sampling campaign in the spring. We'll be doing more this spring and summer to try to understand, based on these existing job sites, how these materials behave. Just as an example, at one site where we had good control on all the variables, sort of similar age, similar aggregate blend, there was just about a 2% difference in gross CDR between parts of the road that were highly compacted and parts that had low compaction. So compaction seems to be an important variable. And gross CDR in aggregate blends that are poor in LMF versus high in LMF, we see sort of a 2 to 3% difference as well, and at a site where we had similar characteristics otherwise. So those are just two examples of things we've started to learn from the field. We're excited to keep learning more, and I think for now I'll kick it over to Sean to talk a little bit about our commercial progress. And yeah, so
awesome.
Sean.
Thanks, Dan. So as Megha mentioned, I've spent the last 25 years in business, but really at the core, I'm a geochemist. I was working on essentially this problem back in the 90s, chemical weathering and its impact on the inorganic carbon cycle and atmospheric CO2 at Berkeley, as well as paleoclimate work. And really, for the last 10 years, I've been kind of bugging former colleagues in the science space about when things are going to start happening. Now, the exciting thing is there's a lot happening, as everyone knows now, in the CDR space. And really, I started working with Dan about 2021 when I literally saw that he was working on ERW field trials at Carleton, just up the road from me. And I'd gone to Carleton as an undergrad. So I reached out to him. We started talking. And after a couple of successful field seasons, we decided to launch Alkali Earth in the fall of 2022. Initially focused on ERW and agriculture using slag. We could tell slag was a really, really powerful CO2 scrubber. But as we got to know our supply partner, we're working with a major steel slag producer. We started to pivot towards gravel roads, realizing there's, as Dan mentioned, huge markets for aggregates and a lot of room to optimize, but also really that ability to measure simplifies things a lot. So in last spring of 2023, we signed an exclusive relationship with this supply partner. Over the summer, we started working on pre-purchase contracts. We're lucky enough to win the Frontier contract, selling to Shopify and Stripe in early fall. About a month later, we deployed our first project in Ohio, which was exciting and kind of gave us momentum. But then coming into the fall, we turned to focus on fundraising as well as optimization experiments and planning for 2024. So where we are now, we're really focused on a number of things: team building, launching our R&D site, and scaling our deployments this year. Next slide. And really, I think one thing that's critical is we're starting with a really exciting use case, but we know there's a lot of room to optimize, right? And so the R&D program is really critical to making the best use of slag, which we think is a great source of alkalinity. To this end, we're launching a Sentinel site in Q2 this year, which will be highly instrumented, allow us to measure a lot more about what's going on within the roadbed. So specifically gas flux measurements to measure the amount of CO2 coming out of the atmosphere and the soils. Solute phase measurements to look at cation loss from the aggregates. And then changes in the solid phase, the accumulation of carbonates and the loss of cations from the original slag materials. And really what this will let us do is focus on optimization of CDR and aggregate roads, but also to test new deployment strategies and really new use cases, as well as new materials over time. So next slide. And the other big question that we're really focused on day to day is how do we ensure additionality while driving scale? And really the way we think about this, it comes down to first expanding the markets for slag. These tend to be very localized markets and not all the materials are used optimally. So expanding the markets through subsidies is the starting point, but then really we need to divert materials from low carbonating use cases to high carbonating use cases. In some cases, that means mining legacy materials, which tend to be fairly unreacted, and many steel mills have giant legacy piles, but also developing new use cases and optimizing the current use cases. So in general, we're trying to make sure these materials are used as well as possible for carbon capture. Next slide. And going into 2024, we feel incredibly lucky and excited about the traction we've got. There's a lot of work to do, but first we need to finalize our funding agreement. This will give us at least 3 years of runway. but is likely to close in the next month. We're continuing our laboratory work to help develop optimization strategies, but really very excited to launch our Sentinel site in Q2 to test new optimization techniques and new use cases. Also critically, we're going to start building out the team. We've been very, very lean to date, but we're starting with a senior scientist and a head of business development. If you are interested or know folks, please reach out. So we're actively hiring now, and we'll continue to build teams below those folks. And then finally, we need to deploy at least 40,000 tons of slag this year to satisfy our current commitments. We have won a couple of other purchase agreements that I forgot to mention. So we're on the hook for at least 40,000 tons of slag this year, with a stretch goal of up to 100,000 tons to start entering the post-purchase markets. So anyhow, very excited, happy to take any questions, and thanks for the time.
That was excellent. Thank you so much, Dan. Super clear explanation of the chemistry, which I think is always helpful to be refreshed for us non-chemists. Are your other pre-purchase agreements public, or are they non-public?
Not quite public yet. There's smaller add-ons, but it's good. We're obviously everything's an exciting point of traction. So
we'll stay tuned. Just wanted to see if we could break some news here. And so you guys talked a little bit about, both of you, about sort of how you came to mineralization, and to some extent about the formation of Alkali Earth, how you guys got together. Can you recap how you moved from just like the rationale and thought process of moving from deploying slag on working agricultural lands to the gravel road idea, just to kind of reinsert that?
Yeah. So I didn't maybe give as good of a background as Sean did for myself, but I'm a professor at Carleton College, and I have academic research on enhanced rock weathering in agriculture, and have been working with basalts and with steel slag in those projects, and started that during sort of as a COVID sort of pivot, and getting interested in CDR, and started learning a lot. Sean and I started talking, and we went round and round for a long time trying to evaluate how we would build and launch projects with, using slag and in more commercial scale projects for ERW. And honestly, we're struggling with the measurement part of it. And I know the industry since then, that was 2 years ago. Since then, we've learned a lot. There's, more people, there's a lot more people working on it, a lot of really smart people working on it. So there's been tons of great progress in that direction. But at the time, we were felt like we were on a merry-go-round, and we had approached the company that's now our supply partner, and realized we had a lot to learn for how slag was being used in industry and in aggregate markets. And I think from my academic perspective, I have often thought of slag as sort of a waste product, like, oh, it just accumulates and no one does anything with it. And that's really just not true. It's used in a lot of different applications. So as we started to learn more about that was where we realized, oh, there's this pretty huge opportunity in roads, and we felt like no one else was really thinking about it. Certainly the material handling companies weren't that's not really their business to think about that. And so we felt like there was room to optimize, and really the measurement, what part of it was what unlocked it for us, was we felt comfortable building a project we could sell because we could directly measure the carbon removal.
Yep. That said, though, I think ERW in agriculture is a great use case. Soils are good reactors. Yeah. They're just open systems, so they're hard to measure. When there's better consensus, slag is great in agriculture too, right? There are slag-based liming agents already that are approved by the EPA and USDA. And so we'd be happy to come back into that space if it makes sense. But for now, we're starting simply and practically. And we think of aggregate roads as an MVP, right? The economics are good enough to get going, and the measurement is quite clear. One comment on uses of slag. So in the US and in Europe, mostly slags get used somehow, right? Some high carbonating uses, some low carbonating uses. In the developing worlds is much more variable, right? And so some places there really are large accumulations of slag that don't get used. And so that's a major opportunity as we scale to go overseas and start to access these large legacy piles.
Well put. Thank you. So on the scalability question, from your Frontier app, which I put a link to that in the chat and super helpful to read. Sorry, I lost my screen. So currently in the Frontier app, you said that there's roughly half a gigaton a year of slag produced, and your carbonation rate is 0.4 tons of CDR per ton of slag. And then I think based on the Phil Renforth paper that slag production could reach 3 gigatons per year by 2100. Are those numbers correct?
Yeah, I think so. Yeah, and we're asked this question a lot, and I think it's an important question to ask, and it's one that everyone should be thinking about, is how do we get to these numbers that we need to get to by the mid-century or the end of the century? And I think, if I remember right, I could be misremembering, but I think the timeline for Frontier was 2100 or to get by the end of the century. And so a couple of things are worth pointing out. One is that steel production probably is projected to increase. That's why that number that you're right, that was from the Renforth paper, that the steel industry is probably going to grow. Hopefully it decarbonizes. So as we produce more steel, there's no way to produce steel that we're aware of that you produce steel without producing slag. So even as the steel industry decarbonizes, we're still going to be generating these materials.
Yeah.
And so we'll be producing more slag in the future than we produce today. Almost certainly, at current rates of production, there's not enough actively produced slag to reach a half a gigaton.
Yeah.
In the future, there could be. That 0.4 number is also sort of more of a potential number. So in reality, the realized rates of removal are lower than that. So unless, as processes optimize, you'll get up closer to that, but probably never truly achieve that number within the framework of an LCA. And so it's just an exceptionally hard challenge, obviously, to reach half a gigaton or gigaton scale. We feel really good that this type of an approach and utilizing steel slag certainly could reach the hundreds of millions of tons, which is a meaningful, in our views, is very meaningful. And this material is generated every year. There's large legacy sources. So trying to better understand how to utilize it for carbon removal, we think is definitely an important mix. Whether or not projections hold true is anyone's guess, I guess.
And I think one other thing that we think about a lot is there are other sources of alkaline materials out there that may become part of the portfolio. Right. But again, we're starting where we have the lowest hanging fruit, right? Simplest approach, very reactive.
Once you learn how to do this, you can work with other feedstocks, other deployment surfaces. Yeah, I completely agree that this idea that everything has to be gigaton scale is a red herring and unhelpful. And not everything will be. And I think there are a lot of good solutions out there. So on the deployment side, so you talked about other deployment surfaces, like you could potentially deploy your, if once the MRV is more established, you could deploy to working lands, which are much less limited. I hadn't seen any estimates of like how much road surface is there? Like what is the scale potential for gravel roads in the US and globally?
The markets, from as best we can tell, the markets are much larger than there's not enough slag to satisfy the markets. So the shortage would come at the finding slag rather than finding places to deploy it. So I think my memory is, I hate to say this and be wrong, but my memory is the aggregate industry of crushed stone, that would include slag, is like 1.5 gigatons of crushed stone a year. Obviously, not all of that goes to roads, but roads is a sizable part of that as well. And so there's, hundreds of millions of tons of aggregate being used every year, and that's just in the US.
And if 0.4 is if 0.4 is the ideal carbonation rate, like what's the current thumbnail? Is it like 0.2, 0.25?
It depends on the time scale. So say over 10 years, we'd be approaching 10 to 15%, depending on the job. And that's part of what we're trying to understand. And those are, depends on I mentioned in the talk how these job sites have various characteristics that we've been able to visit. So that's kind of our rough guess, but we've only been to a couple of sites so far.
Got it.
Right.
Sean, sorry to interrupt you. What were you gonna say?
Oh, never mind. I forget.
Let speak up if you think about it. We'll rewind. So on the like moving to MRV, so to what extent is everything directly measurable in your process, and to what extent will you be relying on modeling, and will that change over time as you learn more and have more experience?
Yeah, so where we're starting at today is we're making so we can deploy a job, so we can take samples of the material when it's produced and when it's deployed, and then we can return after a year to collect samples from the site and get a 1-year carbonation number, and that's based on direct measurement. We can also go back to that site in 2 years or 3 years or 5 years. There's economic trade-offs based on the carbonation rate slows down over time.
Yeah.
So that first year we know is a big enough bucket to build a project around. And then it's sort of to be determined on which intervals will return to jobs to get additional sort of vintages of credits over time. But our approach now is to measure everything. So everything we're selling now and deploying now, we're planning to measure. As we look over the next few years, we envision creating a large enough data set of carbonation rates over time for certain types of materials and certain types of locations, such that we could pivot to a model where we basically have a statistical model. So not a like reactive transport model or something, but just a simple statistical model that we can use to predict carbonation and then audit some amount of jobs within an area where we're using that predictive model. And so part of the reason of measuring everything now is that we're building that robust data set to underlie the statistics that we'll plan to use in the future, where we would have more of a prediction and auditing or predict and verify model.
Yeah.
And I think it's worth saying that for any mineral-based approach that uses land, that has to be the case, right? You have to get to a place where we can work more on an audit basis than an intensive measurement basis for it to scale.
Yeah,
that's out in the future.
I agree. There are a few measurement zealots out there who might disagree, but I think that's the practical reality.
Yeah.
So I had one question about additionality, and then another one came up during your presentation. So I guess 2 additionality questions. Number one, how do you attribute the CDR and the carbonation to the materials that you're adding to a road versus what might have happened had you not added your materials? Because the roads do carbonate themselves on their own, right? And there's some carbonation or carbon removal that would happen from a no intervention road.
Yeah, the slag-based road. Yes.
Yeah. Well, Sean, why don't you hop in?
I think it's more about ensuring that we're taking materials from non-carbonating uses and a few that are out there, right? So some of the materials sold in very large chunks, think golf ball to softball sized chunks.
Yeah.
We just know there's not enough surface area for those to react significantly. There's other uses that are essentially buried or covered in asphalt that are non-reactive. And then there's the legacy piles, right, where they tend to crust over but not react in the core. And so part of additionality is ensuring that we're taking material from non-carbonating uses to carbonating uses. But then within the carbonating uses, in all honesty, right, roads don't dissolve fully, right? So there's room to optimize how much carbon capture there's in the road through things like grain size, level of compaction, the blend of materials we use, and other factors. In addition, we're looking at other options too, like reactivating the same materials by regrading the roads in the future, right? And in particular, one thing we think about talk about with our partner is most steel mills are surrounded by millions of tons of slag just on their own sites, right? And so starting to reactivate those sites can create additionality. So those are kind of near-term opportunities. Then longer term, there's novel use cases, right? So agriculture is pretty prominent for steel slag, but then there's other ideas we're exploring as well.
Got it. So that's the additionality from the feedstock. So the feedstock potentially carbonate no matter what you did, and other if in business as usual situation. Is there any carbonation that's happening from the roadway if you're not applying slag that you have to worry about from an attribution perspective, or is the way you're doing your measurement getting only your intervention?
So I'll say one thing maybe, and I'm not sure I understand part of it, but though with each scenario that Sean was just laying out, like utilizing legacy material, or if we were to do an intervention with an existing roadway, in those cases, one of the things we're working on right now is baselining the scenarios. So we're sampling and measuring chemistry on legacy piles, for instance. And so those materials, we can get a baseline set of information on, so that when we take them and process them and put them in a road, we can compare the baseline chemistry to the chemistry of the road once it's been sitting and deployed for a year. So I think part of that comes with proper baseline. And in the case of an intervention, we could sample the site or the project where we're going to do the intervention to get a baseline to understand what was there to begin with, and then leave controls that we don't do interventions on as sort of what would happen over time in the absence of an intervention, if that makes sense.
But I think is part of the question, what happens if the road is, say, a crushed limestone road, for example, instead of a
That's what I was getting at and not articulating well. Sorry.
So,
Got it.
So in that case, a crushed limestone road is already calcium carbonate, which is the end state we're trying to achieve. So, I think there's arguments that may create some amount of CDR if the road dissolves and you're essentially taking up another bicarbonate in solution temporarily, but that's it's hard to achieve, in our view, true permanent CDR by dissolving and then limestone, for example, right? So you might get a temporary effect, but not a permanent effect.
And I think it's also worth saying that one thing we are concerned with is contamination in our roadways. So if we're measuring inorganic carbon, did that inorganic carbon come from limestone that was underneath it when we applied the slag? And so one thing we're doing as a starting point is we're not doing any projects where the materials blended in with an existing roadway. And so we're only looking at homogeneous layers of laydowns where we put the slag down. So it's not mixing with anything.
Yeah.
Okay. And we've been doing some additional sort of measurement to try to understand using isotopes if there's any way to trace contaminated carbon sources, for instance. But
cool. Sorry for not being clear with my question, but thank you for.
No, that's okay.
So I was, definitely want to talk about potential negative externalities and toxicities, but there are a couple of good questions about that in the audience Q&A. So I think let's keep those for there. One last question for me. So how do you approach the commercial challenge of the fact that the carbon removal from your approach occurs over time? So it's not like direct air capture, capturing CO2, putting it underground. Right. You're not the only approach that has this challenge. Other mineralization, enhanced weathering has this challenge. Certain geochemical marine CDR approaches have this challenge. So there's an MRV challenge, and there's sort of like a commercial challenge relating to when does the credit get generated. And I don't think the market has exactly decided the answers to all these questions, but how do you think about it? Like, because, Frontier may not care because you're doing a pre-purchase and it's an innovation. It's designed to encourage innovation. But like, as the sector matures, what's your view on how that will work? Will your credits not be generated in 10 years? Or like, how do you see that happening?
Yeah, so let me take that one. So the good news for us is we get a lot of uptake in the first year, which is essentially enough to pay for the project and build a business around. So we certainly envision measuring it 1 year. We believe it's going to be economic to measure out to 5 years, but essentially our model is selling tranches, right? So a given deployment might generate tranches of CDR at 1 year, 3 year, 5 year. There's an open question, right? Going out to 10 years, there is still additional CDR happening. It's just a question of, is it worth it to go after that tail, which is somewhat asymptotic. But we know that it'll continue to deliver. And in fact, again, we think that these materials over deliver, right? There's probably some leachate that's coming out of the roadbeds that represents additional CDR over time. And these materials will continue to react until they're fully dissolved in, a century or so, right? So they will continue to over deliver. It's really a question of how long is it economic to measure.
And you had this chart, I think, in your presentation. Can you remind, like, how much happens in year one and how much happens in the first 5 years of the notional CDR?
Yeah, so in year one of the CDR we can achieve over like a 10-year period. It depends on how variable it is, but probably half to 3/4 of it can occur in the first year. So the first year is the most meaningful sort of tranche of credits to measure.
Yeah.
And that's kind of how we're scheduling projects right now, is we're delivering that first year of credits. And then in our projections that Sean's smarter at thinking about than me, like, we can sort of evaluate as projects sort of build up and age, we can plan to revisit to measure additional credits over time that we can deliver beyond that first.
You could potentially have a phase 1 at year 1 and then a phase 2 at year 5 or something.
Yeah,
That's right. That's right.
Got it. And very interesting. Cool. Plenty of more questions, but we have some good audience questions. So maybe Megha, if you're ready, you can hop on and ask some of those. Thank you, guys.
Sure. Yeah, lots of great questions. The first one I'm going to ask is just in terms of the actual reaction kinetics, how much do you or can you control that? And so I think the questions in terms of things like particle size, which you touched on, but also just the environment of different roads, different locations. How much control do you have there?
Yeah, so never as much as you'd like, I guess, is the quick answer, but there are things we think we can control. So obviously particle size is one thing. The blend, creating a really reactive blend. One thing that's important to point out is there's sort of trade-offs depending on what the project's being built for. So we use the term gravel roads because it's a very, everyone understands what a gravel road is, but there's lots of different, if you're building a road or you're building a parking lot, or you're building, an industrial yard that's going to be driven on, it depends what they're going to use it for. And they're all kind of looking for different levels of stability in that surface. And so you can't always control everything as much as you want, because if you want to make it perfect for carbon removal, you're going to have trucks like sinking into the road because it'll be kind of soupy. And so there's trade-offs there. But we're working on understanding how far can you push those variables before you realize negative trade-offs. And then there's also the idea of sort of these materials. This is a passive process, and as you're forming carbonate minerals, you're passivating the process. So you're creating minerals. The carbonate minerals are sort of coating reactive surfaces, and so one of the things we're trying to understand is how do you reactivate that to get that passive process to sort of kick back in. There's obviously a lot of people, working on more engineered approaches, and we think those are awesome too. We sort of favor working on these passive approaches because of the lower energy intensity. And so we're trying to figure out, smart low energy interventions to use in terms of holding off that passivation for as long as possible.
One of the early learnings from our field work last year is that compaction slows down the carbon capture, right? There's just less pore space. And so part of what we're looking for in novel use cases this year, where they're industrial gravel surfaces, but don't have much traffic. So think about things like battery storage facilities that use gravel for the grid, and battery storage tied to factories and data centers and so on. So we think there's opportunities, use cases that are very similar to what we're doing today, but just not having significant traffic on them can significantly boost the carbon capture. And there we may have more flexibility with things like grain size and mix also.
Got it. Okay. And then in terms of then the downstream effects of that. So a couple of people asked about the runoff, what's in it, what kind of issues do you potentially foresee, and how do you mitigate that if that's a concern? Yeah.
We've gone, had the same thoughts and concerns and are monitoring it and everything that we're doing. one quick thing to say, and I forgot to say it during the talk, but is that slag aggregates are used across industries and across different markets, all across the US and in Europe and in a lot of different places across the world. And so generally it's accepted as being safe to use. And all of with our supply partner, they have a pretty strict sort of quality control process. So everything is screened. There's, different types of procedures, EPA leach tests that are done to make sure that the material's not leaching anything hazardous or toxic. And they don't even really contain those metals to begin with, because there's quality checks in the steel mills at this point too. And so I do see one comment in there about how sort of as at high pH metal mobility can change, and that's certainly something we've thought about. At our research site, we'll have instruments installed to look at leachate. So that'll be a nice new learning. From everything we've looked into, we feel pretty good about that not being an issue. But it's something we're continuing to monitor. Obviously, doing no harm is a key sort of principle with CDR, and we want to be good practitioners for that. And so, yeah.
Dan, the one thing I'd add is I think the strongest safeguard is that the slag processor actually tests every batch coming out of the steel mill while it's still in molten state. And so if there's any metals of concern, they don't accept it and they send it back to the steel mill. And so
Got it.
that front line of that first line of defense is probably the most important one.
Got it. Okay. Just turning to, I guess, the MRV a little bit. So how much does the sort of rate and the amount of carbon capture depend on the environment as well? And that could be like the sort of moisture content and things, but also things like the traffic that you mentioned affecting capture rates.
So one thing is we don't 100% know yet, but we're very excited. So we have big plans this spring to sort of visit sites all along in different climates, basically. So from the Midwest down through into the Southeast. And we're really excited to see sort of how much variability we see with similar materials. We know moisture is an important component to increasing the rates. So that could be up to some point, and then maybe there's more leaching that happens through the road. And so we're not 100% sure, but that's one of the main things we're working on understanding moving forward.
In our reactor vessel tests in the lab, we do know that moisture is a huge driver. It's just we don't control that except by the locations we choose.
Got it. Yeah. Okay. Great. Then we had a couple of questions that were almost more logistical, but like in terms of the slag being transported to its final endpoint, which I guess will happen along miles of roadways, do you have a sense of how far you can kind of get transporting it before you start to lose out on the net impact, I guess, because you've transported it so far at that point?
That's a great question. We spent a lot of time on this, and the short answer is slag, like every other aggregate, is transportation limited. And so typically the transport from the processing facility to the end use site is the biggest driver of emissions. But the economics limit distance faster than the CO2 emissions do, right? And so the economics today, most slag is sold within 25 or 30 miles of a steel mill. That's the point at which the transportation becomes more expensive than the material itself. And you're always competing with natural rock, right? So what we're trying to do is essentially double that radius from, say, 30 miles to 60 miles. And we can do that through a transportation subsidy. Doubling the radius from the steel mill essentially quadruples the size of the market. So that we feel good about. The CDR efficiencies, of course, also drop the further you go, but they drop not as fast. And so we could still have a very viable project at 60 miles, even up to 100 miles from a steel mill. It's just the economics get worse faster than the CO2 emissions.
Okay, got it. And what kinds of roads do you think you'll be using? Is it like public roads controlled by the government, private? Like, where are you sort of forming those agreements to spread the gravel there?
So most of the roads tend to be county roads, and those are good use cases. They are a big part of what our partner does today. But I think we're more focused on industrial sites where we have, good control over the deployment date, the amount of regrading that happens, the depth of the layer. We just have more control and more room to optimize the deployment. So I think we're focused on large industrial pads, which again are kind of, hopefully 1 and 2 acres plus. So size matters and deployment style matters.
Yeah, and I think related to that, someone asked what does scaling look like in terms of the number of miles of roads that would equate to like a megaton scale or a gigaton scale. And I know you're saying maybe it's not all roads, but are you able to put that in terms that are like a little bit easier to get your head around?
I can start at the other end of the scale, which is a kilometer of road will consume about 1.1, 1.2 tons of slag, or an acre of field at a certain depth will consume 1,500 to 2,000 tons of slag. And so that then you multiply by the carbonation rate, so 1.1 gets you to the removal rate.
Okay.
So we're starting kind of practically at miles, kilometers of road, or acres or hectares of field that we're using.
Yeah. Okay. Well, a little homework problem to go through your Frontier app and work out the math for anyone who's interested in doing that. Cool. Yeah. Just as the last one, what kind of are the biggest challenges when you're looking to scale up, and what keeps you up at night with that?
Yeah, don't you?
Yeah, well, there's plenty to keep us up at night, but I think one thing we talk a lot about is our ability to measure everything and sort of controlling. It's one thing to like build these first projects where we can feel good about how we can control everything, but as you scale up with all these different types of processes that are like open system, you're spreading material. You go from building your first few projects to building, tens of projects, hundreds of projects, and it turns into thousands of projects. And so the data management and ensuring quality, and I think that is something that as we truly start to scale is a huge problem, a huge challenge, I should say, and something I know other folks in the industry are all grappling with as well. But I think marrying sort of the quality of what you can build in one small project with what you need to build when you have thousands of projects all over the world is something that's going to be a big challenge for the industry to sort of wrap our heads around.
Right.
Great. This has been great. Thank you guys so much for joining us and talking about what you're working on. And Toby, back to you.
Thank you. Thanks, Megha. Dan and Sean, that was really fantastic. Super clear presentation, and I'm very excited about what you guys are working on. So appreciate you being with us.
Cool.
All right.
Thank you.
Thanks so much.
And we'll have the recording posted later this week. A couple just quick notes about what we have coming up, if I can get my screen shared here. So excitingly, we have our friend Robert Hoagland coming on next week with special guest host Tank Chen to talk about the CDR FYI 2023 year in review, which was recently published. And I should have that link to it, put it in the chat, and I apologize that I don't. But that's happening next week. And then we also have super excited, the 27th, we have Sean and Dan's 2023 summer Frontier cohort mate Holocene, a very innovative direct air capture company with an amazing CEO, Anka Timofte. So she's coming on, then a few other ones coming up that we're super excited about. So lots coming up on This is CDR. Again, we really appreciate Dan and Sean being with us today. Thank you to the audience for the great questions and for being with us. And we will see you next week with Robert Hoagland and CDR FYI. Everyone be well and have a good week. Talk to you soon.